Well, would you implement those little equations all the time in our code, or is there libraries that handle all the busy work basically?
Some of it you need to implement.
Yeah.
Right. Yeah, like making a quaternion. We'll use the axis angle thing to make a quaternion. Right. So let's just there's position. Okay, so I'm gonna start here. So anyway, I've got a position vector, I've got a look vector, which is 0, 0, minus 1. The up vector is 0, 1, 0, and the right vector is 1, 0, 0. So we just start out with a set of vectors like that, okay? Let's make a quaternion that represents an orientation. So first thing, GLM colon QUAT Q. Alright. So I think if you make a quaternion like that, it makes what's called the identity quaternion. The identity quaternion is like no rotation. And that's actually what in most game engines, the default rotation is no rotation. It's just whatever the object happens to be loaded up in from its local space, whatever the artist made the object look at is what it looks at. So that's the identity quaternion. So let's write a little function here to rotate a vector by quaternion. Let's go GLM colon vec3 rotate vector. Yeah, let's just do rotate vector. Okay, so I'm going to pass in GLM colon vec3 for a vector that I want to rotate, and I'm going to pass in GLM vector v and GLM colon quad q. So what we want to do is return the vector v rotated by the quaternion q. So if you guys remember, the equation for that is W equals q multiplied by W multiplied by q inverse. I'll just call it q I n v. That's the equation for rotating the vector by a quaternion. So we'll write it. The first thing I have to do is make this pure quaternion W from the vector v. Okay, so let's go q GLM colon quat. I'm going to call this W. Alright, so that's the quaternion W. And then the W, in fact, I can probably use the constructor for this, right? I'm sure you can just pass it in. Equals GLM colon quat. Now, the thing that I've noticed is, okay, so we'll try and find W, X, Y, and Z. Okay, so this particular constructor takes them in the W, X, Y, and Z order. I've noticed other APIs like the DirectX API, something like that. Sometimes they take them in order of X, Y, Z, W. So you need to check the order of the parameters if you're making one. So anyway, I said we make the pure quaternion from the vector, so the W component is set to be 0. And then the X, Y, and Z component we get from the vector V. So V dot X, V dot Y, V dot Z. Alright, so that's the pure quaternion W made from the vector. And then I go W equals the vector, the quaternion Q, multiplied by the vector, or the quaternion W, which is the pure the vector. So then we're going to multiply that by the inverse of Q. So to get the inverse of the quaternion, we can just negate the X, Y, and Z. In fact, let's just do something here. So this is going to be Q, I, and V for the inverse of it. And just to show you, you can use GLM colon inverse. And then we can pass in Q, and we'll get the inverse of that quaternion. And when we look at Q, I, and V, we'll see that all that has happened is it's just negated the X, Y, and Z components. Because that's how you negate that's how you negate a normal quaternion, just by flipping the X, Y, and Z, making the minus the X, Y, and Z. So then I have Q equals that multiplied by Q, I, and V, right? And then I want to return GLM colon vec3, and I need to get the X, Y, and Z components from W. So W dot X, W dot Y, and W dot Z. So that's that equation, right? That's we just coded up that equation in C++. So let's.
Where are we normalized?
What's that?
Where are we normalized?
Now I'm going to assume that Q is already normalized. If Q is not already normalized, this won't work. And
You have to normalize the one that we're making.
No. You don't have to. You just have to normalize Q. And it would still be normalized, because all I've done is negated the x, y, and z, so it'll still be normalized. You know, because it's x squared plus y squared, so it will just cancel out the minus anyway, so it should be still normalized, right? Good question. Okay, so let us take, for example, the look vector 0, 0, minus 1, and let's apply a rotation to that. Let's make a quaternion rotation, okay? So GLM colon quat. Let's make a 90-degree rotation around the y-axis, okay? So if I take that vector 0, 0, minus 1 and I rotate it by 90 degrees around the y-axis, what should I get? So 0, 0, minus 1 is pointing down the negative z-axis, and I rotate it 90 degrees, so now it should be probably the left vector, I think. So it should be minus 1, 0, 0. Thinking about it. If my rotation is counterclockwise, and I'm rotating around the y-axis, shouldn't it be minus 1, 0, 0? Everybody agree with that? Okay, let's try it. GLM colon quat, let's call it rot for rotation, is going to be equal to GLM colon angle axis. So the first parameter I pass in is the angle. Now I can't quite remember, is this in radians or degrees? I think it's in degrees. So let's just pass it in 90 for that. Just see if this works, okay? The second parameter is the axis of rotation. So let's pass it in GLM colon vec3, and we'll pass in 0, 1, and 0 for that. So that is hopefully my rotation and semicolon at the end there.
And the way it rotates depends on the
Say again? In other words, the direction of
yeah,
rotation.
the direction of rotation depends on your whatever you use.
Yes, definitely. No, it's not to do with the maths, it's dependent on the API. And in our case, we discovered last week that in OpenGL our rotations are counterclockwise. So this is a counterclockwise rotation, right? So that's the rotation. So let me go, look is equals to rotate vector. And I want to rotate the look vector by that quaternion that I just made, rho. And then hopefully at this point I should be able to print out or just check the look vector there. And if I set a breakpoint here and check the look vector, F9, function F9 for breakpoint. And you know what, we'll actually set the breakpoint up here as well so we can see everything happening. So anyway, the point is, like, by the end of this, when I check the look vector, it should hopefully be equals to minus 1, 0, 0. Alright, everybody, does everybody understand why it should be equal to minus 1, 0, 0? Just implemented that little equation up there that was talking about earlier. Okay, so function fy running the debugger. Okay, let's make it build first. Yeah, so what I'll do here is just comment out this code here. Which is just the stuff we were working on last week. I'll try and build it again. Control B. Okay, and then we'll run in the debugger. Very exciting. Okay, so here we go. Here's my quaternion cube, which represents that rotation, which is my 90-degree rotation around the y-axis. So you can see the x, the y, the z, and the w components. And, you know, let's just move through and make sure this works. Then we might just verify as to how that quaternion was constructed, right? So anyway, there's me making the w quaternion, which is the pure quaternion made from the vector. All right, so the w now is taken the x, y, and z components from the vector, and the w component is equals to 0. And now I'm going to make my inverse quaternion. So there's q, right? Q is equals to 0, 0.7, and 0. So the q inverse should hopefully just negate those values. So if I look at q, I, and v, yeah, there we go. So I just have minus 0, which is the same as 0. So it's negated the x, y, and z components, and it's left the w component intact. So that's how you negate a quaternion. So that's what that GLM call it inverse does. It just negates the x, y, and z. As far as I remember, that only works for normal quaternions. If the quaternion is not the normal quaternion, I think it's a slightly more complicated equation for inverting it, but you never need to know. Just go GLM call it inverse. And now W, when I multiply that all together, and then I get my thing out the other way, my look vector should now be equals to, the x component is minus 1, the y component, when I expand it there, you'll see the x is now -1, the y is 0, and the z is 0. So, it has worked. Do you believe me now?
Yeah.
So quaternion rotations work. All those equations that we talked about earlier, they all work. Right? And that's how you rotate a vector by quaternion. So, I wonder, should we do anything else with this? Or should we go and do the last thing, which is quaternion interpolation? Let me think. Yeah, there's one other thing that's just worth doing for the hell of it, right? Before we go and do that last thing. There is, of course, another way to do this rotate vector thing, isn't there? I could take the quaternion, I could make a matrix out of it, and then I could multiply the vector by the matrix. That would be the same job. And I should hopefully get the same results. So let's try and make sure that we get the same results when we do that. So this time it's going to be rotate vector, I'm going to call this rotate vector M for rotate vector by a matrix. So let me get rid of all of this code here, okay? And the first thing I want to do here is I want to take that quaternion cube and I want to make a matrix out of it. So if you remember how that works, right? GLM colon mat 4 is what we use to represent the matrix. M is going to be equals to GLM colon, isn't it quat underscore cast? Yeah, quaternion casts.
Is that mat 4?
No, it's the other way around. It's mat 4 cast, right? So you pass in the quaternion, and that is going to make you a matrix which represents that rotation. Quaternion. And then if you guys remember last week how we actually transform a vector by a matrix, GLM colon vec3, I'll call it rep for return value, and then let's say rep is going to be equals to GLM colon vec3. So the first thing I have to do is make a vector 4 out of the vector that I'm passing in, because I have to set the last parameter of it. So GLM colon vec4 v comma, we set the last parameter to be 0 or 1. Which one do we set it to, or does it matter?
1, because 0 just multiply itself by 0.
Think again. 0 or 1 affects the last column. Sorry, the last row.
So you have to do it as 1. You don't have to, but you should, because if it gets multiplied by 0, everything else is 0.
Yeah, it actually doesn't matter in this case, right? But really we should be setting it to 0. And the reason why is because we're not doing a translation, we're only doing a rotation. So if there happens to be any translational part as part of that matrix, we don't want to include it. We only want to do the rotation bit. But you know what? It won't make any difference this time, because the matrix is made straight from the quaternion, so there's no translation part of it. If I put 1 in, it would do a translation and the rotation, whatever. If I just do 0, it would just do the rotation part. So let's put in 0, and then we want to multiply that by the matrix M. And I think that's the right order that you do it. You take the vector multiplied by the matrix versus the matrix multiplied by the vector. Can you guys remember from last week?
No.
I'm sure I have it here. No, it's M multiplied by the vec4, so it's this other way around.
So you're saying that 1 is 0, doesn't matter if you only look for rotation, is it?
Yeah, but there's two. They're called transforming a normal or transforming a transform normal or transform position, I guess, right? So it just, usually if we're just doing rotations, we set that last parameter to 0. If we're doing positions and rotations, we do. So I think that's the way we should do it there. So now, that's the same kind of job, and then we should return the return value. And hopefully we'll get the same answer when we rotate the vector this way. So I've taken the quaternion, converted it to a matrix, and then done the operation on the vector, right? So let's go again. Look is equals to GLM. We'll set it back to be its kind of default value there. So 0, 0, minus 1, and then we'll try look equals rotate vector M, which is that the other little function that we just wrote there. Look at rotation, and hopefully when we get down to here, we'll have again that same vector, okay? So we should end up with minus 1, 0, 0 again, right? So let me choose stop debugging there. Shift Control D, build succeeded, hit F5, function F5. So here we go, rotating the vector this way. Now I've rotated the vector with the matrix, and I end up with the same answer. But happened. It's interesting. Look at the x, y, and z components now. So we just get a little bit more floating point error using this approach, because I've converted from the vector to the matrix, which is maybe going to introduce, the quaternion to the matrix, which introduces maybe a floating point error. And then I'm multiplying the matrix by the vector, so I get another little floating point error. So now instead of getting -1, I get minus 0.999994. So it's essentially the same number, that's -1. Okay. And for this z component here, I end up with minus 5.9 multiplied by 10 to the power of -8. So it's essentially 0.
What's the floating point there?
So floating point numbers they're only 32 bits, right? So like if you were to do, the classic example is if you take 10 divided by 17, okay, and then you add the resulting number up 17 times, you should get 10. But you actually get 9.999. And that's because the number loses precision and it can't actually accurately represent the number with the appropriate number of decimal places. So that's why we can never really check for equals. You know, we always check to see if the two numbers are almost the same. So you can subtract one from another and see if it's less than a really small number, then you say that they're the same. So we get floating point errors. By the way, is there an implication for floats and currencies?
Yeah.
Have you thought about that? What's the implication?
Well, I mean, lots of tiny loss of currency.
Sure.
You know, banks that do millions of transactions a day.
Absolutely. Yes.
you know, end up losing.
So, do you use a float to represent numerical quantities like currencies and
No, there's
transactions?
what's the name of it? There is a specific type, isn't it?
So most languages have specific classes for dealing with currencies which do not use floating point numbers. Floating point numbers are for mathematical operations like sine and cosine and these sort of things, right? They're not for currencies. Currencies in Java, there's a special class called a big decimal. And C# has a built-in currency class which is specifically for currencies. Alright? So, yeah, so now we know how quaternion notations work. Do we all know how quaternion notations work? Does everybody love quaternions? Like, when you're at your fancy dress party over the weekend, you just see some beautiful girl, just get into a conversation. Hey, baby, I don't know how quaternions work. Let me impress you this. Just get your whiteboard marker out, okay?
I ignore the floating point.
Yes, and then you can even say, hey look baby, you see why this? This is because of floating point numbers. I know why this happens. I'm so intelligent. Feel my massive brain. The last thing we need to know about quaternions is the whole interpolation, right?
Maths and cohorts. Home alone that night. Go to your wife and mention it and go home.
Okay, so quaternion interpolation is the last very, very important thing. So earlier on we looked at this equation for the linear interpolation, which is C equals A plus B minus A times T. And that's about the simplest kind of interpolation. You can use that to basically get something which is halfway between 2 points. If A and B are vectors, then C will be a vector, T is a scalar. Okay, so you can get a point which is like a percentage between two other points. One of the great things about quaternions is quaternions have this thing that you can do in this operation called a spherical linear interpolation. And that's the equation for a spherical linear interpolation, right? Slurp. Slurp, okay? Again, this is just the equation in case you ever need to implement your own quaternion class. But there's an API call that you can basically give me a quaternion which is halfway between two other quaternions. And this is how it works, right? In code, what we use is this API here called, which is just gln : mix. So you pass in quaternion A, you pass in quaternion B, and you pass in a value for T.
Would T be
This is
the
one of the
time
most
delta?
important uses.
Would T be the time delta for this?
You could use time delta, it probably wouldn't be, because what T needs to do is it needs to go between 0 and 1. So if T is 0, you get the first quaternion. If T is 1, you'll get the second quaternion. So you might use the time delta to calculate T, but it won't be exactly T. Do you follow?
Yeah.
Like here's a simple example for you, right? Imagine that I had a quaternion representing this orientation and a quaternion representing this orientation, and I wanted to move between those two orientations, but I wanted that to take 3 seconds. So 3 seconds is one of my parameters. The other parameter I have is the time delta. Like what would what would that look like? So if you think about it, you need to get you need to get t to go between 0 and 1 in 3 seconds, and you have the current time delta. So what would your little maths look like to calculate the, what t value you're using? So hang on a second, think about this. This is quite simple, right? At time 0, t is going to be 0. At time 3 seconds, t is going to be 1. So, does everybody follow that? After 3 seconds, t is going to be 1. I know what the time delta is each frame. So, how do I calculate what do I add to t every time? 1 divided by, it's a little bit more than that. It's 1 divided by 1 divided by 3 multiplied by the time delta. Isn't that it? Yeah, no, think about it. It has to be. Okay, imagine I wanted to go, from 0, from quaternion A to quaternion B, and I wanted it to take 1 second. The time delta, if 1 second has elapsed, then that means t is going to be 1. So in this case, t is equals to, I just add time delta to t. But in this case, if I wanted to maybe take 3 seconds, I take 1 over 3, because it's now going to take 3 times as long. And then I just multiply by the time delta. So that's how you go from, the time delta to calculate the value for t. So you can say how long does it need to take, and that's the same way we did the sine problem at the start. I wanted to go from 0 to pi in a certain number of seconds. So I take pi divided by the number of seconds and then multiply by the time delta. Is that all right with everybody? So everybody knows how to use this API call. So there is a lab that I'm going to get you guys to work on next week, right, to do with quaternion rotation sequences. And in this lab, what will happen is I will give you a spaceship which points in some 3D, orientation in the scene. And then I will say, give you another spaceship in the scene which you can move around using the mouse X and Y, using the keyboard X and Y coordinates, you can move it to the scene. And then when you hit the space key, you want to get this to rotate so that it points at this one. But it has to happen over a certain amount of time. And in actual fact, it has to happen at a certain speed. The speed is going to be given in radians per second. So it's a slightly more complicated one than that. So that's just slightly more complicated in that when you calculate the angle, you need to know like that. I can't quite remember how this works. I need to look it up. I wrote it recently. So anyway, you're going to calculate the angle that they're going to have to rotate by. You've got to calculate the axis of rotation. You've got to calculate then what you need to add to t, and that's the problem. Okay. So that's kind of it on quaternion rotation sequences. All right. You can knock off the video there because there is one last thing I wanted to talk to you guys, and that's just about the assignment.